Okay, so we are back at it again. The last thing I was talking about, the ADTs. We have defined a very loose rational number ADT, and what I did in there I didn't realize is that you couldn't see this part because I was blocking your view. It just didn't occur to me. I'll try to keep that in mind, and I'll also share this these notes as PDF, so I don't think it's going to be so much of a problem. It's just that it was hidden with my inset, my picture in there. Okay, so coming back to designing a data type, what we're going to do right now is that moving on from ADT, we're going to move on to something called, oopsie, I lost it again. Yeah, moving on from ADTs, we're going to go into something called a class. So what's a class? A class is just a blueprint of a data type. Okay, so it pretty much defines how the data type is going to be like, and what sort of operations you can perform on it. So if you look at any programming language, I mean, you get some primitive data types. So if you're coming from a C background, which for most of you, that's going to be the case, you will have data types that goes like bool for true or false, and you'd have int, short, long, all these integer data types and their variants, and you'll also have floating point data types like double and float, right? So these are pretty common. What if you need something else? For example, for our rational number data type, there isn't any data type in C or not even in C++ that lets you create rational numbers. How do you go about creating that? Right? This is where classes come into play. Because you got to tell that these are the data members which are going to be in there for any rational number, and what are the things you can perform on any given type. So for example, if you're looking at the int data type, you can do addition, subtraction, multiplication, division on integer, short, long, double, and float for all of them. But if you try to do the same thing on bool, can you do that? No. If you got a boolean a equal to true and you got a boolean b equal to false, you just cannot do any addition operation on it. You can do and, or, exclusive or, those kind of things, but you just cannot do the arithmetic operations on a Boolean data type. So for some data types, some operations are allowed, and some data operations are not allowed, and some are very specific to any given data type. Now, for the rational number data type, when we look at what we have created, it was in page 2, I think. If you look at it, we define that we can do add, we can do subtract, multiply, divide, and reduce, but we never said what's going to be the output of any of these, or we didn't even say like what are the input, what are the parameters that you're going to pass. We didn't say any such thing. We also said that we need to store the numerator and denominator, but we didn't even say how you're going to store them in what kind of variable. Okay, so all these things, if you look at the ADT, this is very much loosely defined. It's not telling you anything about the data types. It doesn't even tell you about the input output for the methods that you have. And that's why it's not going to take you much further. If you're thinking about any programming language, you have to be a lot more specific than that. The conceptual models, they're fine and dandy, and this is a good starting point, but it doesn't really take you to any source code. Okay, so this is where, when we create our own data type, the class, this is where we start becoming more specific. Let me write this down. So we are going to create this rational number data type. Okay, this is again going to be a design. This is a model. It is not something you can write on your computer as a program, not yet, but this is a good starting point where things start to get a little bit more formal. So we again say that we need a numerator, and we also need a denominator. Okay, but this is when we become a little bit more specific. We say that the numerator is of integer data type, and so is the denominator. Okay, and then we say that these are the only two things you need for the data structure itself, the attributes, so to speak. I mean, it has so many different names. Okay, attributes or abstract data structures, these are just a few of those. So we got the numerator and denominator, and we need to put some more stuff, which I will do in a bit, not right away. We also need to say that for operations we have to support add, and if you think of it, let us try to write a little bit of a program. Let's say we want to declare a variable called x. We can say int x equal to 10, right? We can also declare int y just like this, and later on we can say y equal to 20, and then we can declare another variable int z and say z is equal to x plus y. So we got 10 in here, we got 20 in here, 10 plus 20, that gives you 30. We stored that 30 in z. Now if you think about this, and let me make it a little bit smaller because this is not what I really need. It's just to give you a context. Okay, so that's my example, and just in the same way, if I think about our new data type, let's call it rational number. There is no such thing as rational number. Let's just imagine that int is a data type. You could create that. What if in C++ or whatever language you're picking? In our case, it's going to be C++. So let's say we have a rational number called x. Okay, and this is where I want to write it as 1, 3, and I'll tell you what that means. We have another rational number which is y, and for y I want to store 1, 5, and then I want to say rational number z is going to be x dot add y, and can't forget the semicolon, right? So that's that. So we got pretty much a similar scenario. We got a variable which was of int type, we got another variable, we got x in here, we got y in here, and finally we got z, which holds the result of addition. Okay, if you try to compare this with what I've just written, we got rational numbers, not integers. We got rational number x, we got rational number y, and we got a rational number z. What really is happening here, I want to write this as x is equal to 1 by 3 and y is equal to 1 by 5. And this is where I want to perform an operation z is equal to x plus y, which translates to 1 by 3 plus 1 by 5. And now we carried out that operation a few minutes back. Again, making the same mistake, so you won't be able to see this in a little bit. So let me move it on the side. The result which we just computed a few minutes back, z was giving us 11 by 15. So that's pretty much it. So the things to realize here is that we are declaring our variables. They're not called variables anymore. They're called something else. They're called objects. I'll talk about it. But if you look at this, they're very much similar. Here we got the variables, right? X and Y, and here we got another variable, Z. For now, let us just misuse this term variable to say that X is a variable, Y is a variable, and Z is a variable. It's just that their data type is rational number here. If you look at this one here, the data type previously it was integer, now we have a different data type, it's called rational number. When you add two integers, you just write them in this way, x plus y. It isn't so different here. We got x and y, two operands, and the operation is called add. So in our case, when we write this add operation, if you look at the parameters to pass, we're not actually passing two parameters. If you closely look at this, we're only passing y. So where do we get x? Well, we are performing this operation on x, so that operand is already there, and on top of it we got something else. So in our case, we need another operand and the data type of the operand. You are probably familiar with this already, that we write the name of the variable first and then goes the name of the data type. So y comes first and then comes the data type, which is the rational number. All right, and the resultant, you should write it right on the side, but I am running out of room, so whatever I was supposed to write here, I'm writing it down in here. Okay, so that's the add operation. That's the entire signature of the add operation. By signature, I'm more of like saying it's a prototype. It's not the implementation of it. It doesn't tell you how you're going to add two rational numbers. It's only going to tell you that, hey, we need an operation called add, and in order to support that add operation, you're going to pass a rational number and call it y, and the result of adding two rational number is going to be another rational number, which is not always going to be the case, right? If you add two rational numbers, you get another rational number, and so is the same thing for the subtract, multiply, and divide operation. If you look at the reduce operation, you're going to take only one rational number. You don't need to supply a second rational number to it. When you reduce it, you again get another rational number. However, you can think about another operation which gives you a floating point value from a rational number, and that will return a double. Okay, what I mean to say in here is that, let's say we got x, y, and z, and for some reason, if I want to say y dot as float, all right, or let's give it a different name. Let's make it let's say as a decimal number. All right, so if I call y dot as decimal, I should be getting 0.2. Okay, that's the desired output. So if you look at this method, if I need to support this operation in here within this rational number data type, what is it going to be? The name of the operation is going to be as decimal. Let me switch the color because the other things are in a different color. So the name of the operation is going to be as decimal, but it is not returning. It is not returning a rational number to me. It's returning a double. Okay, and you'd notice that I haven't written the subtract operation. I haven't written the multiply and divide or the reduce operation. I just wanted to show you that the return type can be different. It doesn't have to be the same thing as the rational number itself. Okay, so there can be more operations added in here. If you look at this box, which has three different parts, let me close this first. Okay, so if you look at the drawing that we have in here, the name of the data type, all right, is here, and this is the irrational number. The attributes or the data structure you're going to store is in this box. So you got two things, numerator and denominator. And the operations that you can perform are in here. So you got add and as decimal, and then there was supposed to be a bunch of other stuff that I didn't write down yet. So this is pretty much it. This is what we call a class diagram coming from a set of diagrams called UML, which you're going to study in depth in many other courses like software engineering course, or your information system design course, or even in your Java course. You will have a bit of UML in there. UML stands for Unified Modeling Language, and this is not really something I need to cover in detail for data structure. What I want you guys to understand is that any data type we talk about, any data structure we build, they will inherently have some data structure or attribute that we are going to store internally, and the operations that we are going to add on top of them, that's what's going to define how you're going to interact with the data structure that we just designed. Okay, so this is our class diagram. We are creating rational number as a data type, and this is what you need to look at, that the example is how it's going to be used in real life. That if you write a computer program, and this looks more like a computer program where you define the variables or objects rather, which I will cover in a bit. So we got the class and the variables or the objects, and this one is the operation that you're going to call to get your calculation done. However, we haven't taught our C++ program how to carry out rational number addition or how to get the as decimal operation. Okay, we haven't defined any of that. So those are the things I want to cover later as a follow-up to this. What I want you guys to understand is just from this example that how you start from an ADT, then you take it to the class, and then we're going to look at the other stuff, how you can translate this into a computer program. When we get to know about that, none of this is related to the data structures that we are going to learn in this course, but we will soon be able to take this idea to create our first real purpose data structure at the stack. Okay, that's where I want to head to, but this is an intro talk. This is the intro to abstract data types, and what we are moving into right now with creating the class diagram, we're moving into classes and objects. That's heading into, what was that? Object orientation, object-oriented programming. Okay, things are going to be a lot easier with object-oriented programming, you will soon see. So that's where we're headed. So let me finish this recording by wrapping this up and saying that from the ADT, what we covered in the first part, we are moving on to the classes in object orientation, and soon we are going to go into computer programs, which is going to be an implementation of this thing. Okay, so let me finish recording here.